over for you. Are you going to be doing this again in the future?
Possibly.
Okay.
We're doing it for Christian. He had something going on today. So.
Let me know in advance, and I will make sure that there's a stand so that you can, and it holds a mount that you can actually put your cell phone in and adjust it in any way you want to.
Thank you.
Welcome. So question 71, it says a Gaussian surface in the form of a hemisphere of radius r, 5.68 centimeters, lies in a uniform electric field of magnitude of 2.5 newtons per coulomb. Is that a normal type of electric field?
No.
Let me define normal. Is this an electric field on the human scale?
Probably not.
I'm sorry?
Probably not.
What would be an electric field on the human scale? What values would we be looking at?
Hundreds to thousands.
Hundreds of thousands. This is more on the scale of what? This is a very difficult question, but you have the ability to figure it out. Anybody?
Electronics.
Yeah, exactly. Probably not even electronics, probably more simple, or just electrical devices, like a capacitor, a resistor, or an inductor, or something of that nature. So that's certainly on this level. So yeah, that's something, that's not important for the problem, but it's something that we will draw upon later on in the semester. So, yeah, the magnitude of 2.5. The surface encloses no net charge. So at the flat base of the surface, the field is perpendicular to the surface and directed into the surface. What is the flux through the base and the curved portion of the surface? And so there's a lot of words there, it requires a lot of interpretation, that type of thing. But basically, this is what we have. This is 12 years of art school. Do you know how long it took me to draw that picture? It's like 20 minutes. And it still looked like it was done by a kindergartner. That's the thing. So, all right. So we have our coordinate system, our X, Y, and Z. Those electric field lines are really sad. The electric field is coming through the base and passing right through the entire surface. Now, this is why, if you go, why would I ask such a stupid question? Okay, here. It's because this is essentially what Maxwell did in terms of envisioning the electric field generated by something we don't know about yet, which is a capacitor. Okay, and we'll explain that idea here. But essentially, it's basically defining the flux through the base, which is coming in this way, but the area vector is pointing out this way. And so the flux under that condition is going to be positive or negative.
Is there a reason why you drew electric field going up? Doesn't matter.
I could turn it sideways if you want, or upside down. Does it matter? I just did it because X and Y are, and Z points up, positive up. So, did it? You,
Perpendicular to the surface and directed into the surface. Oh. Yeah, okay. I get it.
be honest with you, I wasn't even paying attention to the wording here. I just drew it this way. Bless you. So, but is the flux positive or negative through the base?
Negative.
Negative. Why is it negative at the base?
It's just going inward.
It's going inward, and the area vector is pointing outward. So when the electric field is up and the area vector points down, they're opposing each other. The angle between them is 180 degrees. Cosine of 180 is -1. So that's why you get the negative flux. So when it's going in this way. Now out here, the area vectors along the hemisphere here are all pointing at different directions. Okay? This, like off to the side here at the very base, the area vector points along the y-axis. up here it points at an angle of 45 degrees, and then here right at the top it actually points straight up. So the area vector and the angle between the area vector and the electric field is variable. In this case, and if you were actually going to calculate use Gauss's law to calculate something, you would have to keep the theta, the cosine of theta, in the equation, in your integral. Okay, you couldn't just declare it as 1, like we have been. This is going to, you know, the area vector is going to have a variable relationship, and so you're going to have to convert you're going to have to convert your cosine of theta into some kind of physical distance, or you're going to have to convert your physical distances to some kind of angle. It makes it for a more complicated calculus problem. And upper level electromagnetic theory classes, that does happen. Here, that won't happen. Here, you have to envision some kind of trick in order to make this work. And some of you, if you figured this out, you know what that is. The flux going in has to be equal to the flux going out. It's just got a difference of sign on it. Does that make sense? Okay. So that's what we're looking at here. So the flux through the base is going to be E dot dA right here. And so, you know, we got their cosine of 180 degrees times dA, that's -1. So this is going to be minus pi r squared times E. Okay, and that's the area of the circle. And not the area of not the surface area of a sphere. This is the area of the circle. Does everyone understand why that area is there? Okay. So then we just basically take our flux value here, plug in all of our known values, and we end up with a minus 0.0253 Newton meters per Coulomb squared. And then the the flux through the curved portion of the surface, the net flux through the entire hemisphere is 0, because whatever comes in must go out, because it's not actually enclosing any charge at all. So our Q enclosed is 0, so the flux is equal to 0 then. So the net flux here is equal to our flux through the base plus the flux through the curved surface. It must equal to 0, which means that the flux through the curved surface is equal to the negative of the base. It's a mathematical proof, okay? Would I require you to do a mathematical proof? No. Okay, but I require me to do it. How's that? I don't want to throw anything up there without any kind of evidence to back up what I'm going to say. And so I would prefer that you do the same, but mathematical proof is not required for this course. So you can just sit down and go, oh, flux is going in, flux is going out, and everything works. So this is the negative of our negative on top, and so that's what our answer is. No integration, no integrals were necessary, no calculus was harmed in the making of this problem. So, okay, questions? It's a very important principle, by the way, and elegantly simple and profound in its outcome, as we will find out later in the semester, probably towards the end of July. All right. All right, so, this problem is fun. This one right here. An electric field given by the vector, the electric field vector here, 4I hat, and then we have the J hat term where the field is variable. It's not a consistent field, okay, or not a constant field. So it's a function of y, the function of the position y. So you have 3 times the quantity y squared plus 2, and that's the J hat term. It pierces a Gaussian cube of edge length of 2 meters and positioned as shown in the figure. The magnitude E is in newtons per coulomb, and the position X is in meters. What is the electric flux through the top face, the bottom face, the left face, and the back face? And what is the net electric flux through the cube? So, and then in addition, so we gotta go all of problem 2, but then we need to find the net charge that's enclosed by this surface, by these surfaces. How did that work out? Everybody get that? Didn't work? It did? It didn't? No? At all? How many people did it? No? You didn't do it at all?
I got distracted.
Okay. Dare I ask by what? Never mind.
Sleep? I don't know.
All right, so this is what we're gonna do. So, our equation is up on top here. We have our dimensions. I have my area vectors. Area vector this way, area vector this way, area vector this way, area vector to the right, and to the back, and to the front. Okay? So there's gonna be 8 surfaces that we're gonna have to deal with here. Right? Okay. Or 6, I'm sorry. So the flux through the top right here is E dot dA. And so we take our electric field and we dot it into our area vector. Now our area vector in the top is in the y direction, okay? So when you take, and y is at that point is equal to 2. So you basically perform the dot product, okay? You perform the dot product by taking, well, first of all, is 4I hat relevant to the problem? No, it isn't. Okay, you're basically taking, your area vector has a 0 I hat, so you take 0 times 4, and that's it. The area vector here times our y term, however, has a minus sign on it, and of course we plug in the 2. So I basically plugged in our value for 2. That gives us 4I hat minus 18J hat. So that's the strength of the field at that location. And then we dot it into our just our y term. The minus 18 comes outside the integral. And so we can then, at that point, everything is just in the y direction. So you can actually drop the unit vector from the problem. Well, actually, what you do is you multiply j hat by j hat. When you, what do you get when you multiply your unit vector by it's the same unit vector? I don't like that word. Yeah. Just one. Yeah. It's still there. It's 1. And this multi comes to a value of 1. So, bless you. So we get our minus 18, and of course the area that we're talking about is just 4 meters squared because it's a 2 by 2 on the top here. It's a 2 by 2. So you just get the area there. So that gives us a flux of minus 72 Newton meters squared per coulomb. The bottom, the flux at the bottom here is, again, we're going to take our same equation. It's supposed to be a minus sign, I think. Yeah, it would be minus in the j hat direction. And this is at y is equal to 0. So in this case here, we plug in our values. We get our 4I hat minus 6j hat dotted into the negative area vector. That gives us a 6 integral of dA. Notice the closed integration has been removed here because we're only dealing with a singular face. So it's not an enclosure anymore. How is it that everything is still valid? Yes.
I have a question. Where's the 4 I have going again?
I'm sorry?
Where's the 4 I have going again? Like in the first and second?
Right here?
Yeah.
Well, since there's no I hat term, it's basically 0 times 4 I hat. And so it zeroes out.
Okay.
It's a dot, that's the dot product.
Oh, okay.
Does that make sense?
It does, yeah.
Yes.
Why is the DA negative in
Because the area vector is pointing down in the negative y
the?
direction.
Okay, okay.
So, yeah, there's a lot of moving parts to these things, so if there's a confusion, let me know. Alright? So, then we get a cancellation, -1 times -6 gives us 6. This is our integral here, the dA, that's 4 meters squared again. And so then we end up positive 24 Newton meters squared per Coulomb. Make sense? Questions? Okay. So, and then we look at the left face right over here. The left face, again, we have our E dot dA. We have our terms here. This is going to be our minus. Oh, I'm sorry, I was thinking, why did I write J hat, but it's an I hat. Minus dA I hat. So it's pointing in the negative X direction, okay? So that means the Y components in here, those are not, we zero those out, okay? So this is basically going to be just 4 I hat into times minus dA I hat. And so we get minus 4 dA, which is minus 4 times 4 meters squared, which is a minus 16 meters squared per Coulomb. Make sense? No questions? Yeah.
How did the 4 get negative? Are you just taking out the negative from the area vector?
Yes, exactly.
Okay, okay.
Exactly. Everything else making sense? Because there's any missing point of understanding here, it doesn't, in the end, it doesn't make sense. None of it makes sense. So we need to clear these things up here now. Yes?
Oh, no. I was just thinking in my head, it's like, is it the electrical field, is it within the Gaussian surface?
There's something inside that's charged. Now, why the person chose a cube, I have no idea. Because if it's a singular charge, we've established through Coulomb's law that it is an inverse square law, which means that it must be radial, which means that the source must be spherical. That's why every charged particle that we've ever dealt with has always followed Coulomb's law, which is why we've always assumed that they were spheres. And like this right here says that the source charge is probably some kind of cube. So maybe that's the way charges work in Asgard, I don't know. So
Okay, that makes sense.
So we'll see. But so yeah, this is where we get our minus 16 Newton meter squared per Coulomb. The back, that's the left, and then I'm going to do the back. Now notice I don't do the right, because the right is actually going to be the same value, just positive, so we'll take that into account. The back here this is going to be E dot dA here. This is everything in the electric field is basically restricted to the XY plane. The area vector here is in the Z direction, okay? Forward and backward. And so any type of area that we're talking about, there's no flux here at all. And so this is all going to be 0. So that's going to be true for the front as well. Does that make sense? Okay. So we've mathematically isolated where the field vectors are in relationship to the planes that basically make up our Gaussian cube. So we have a summary here. We add up our entire flux here, where we take the top, the bottom, the left, the right, the back, and the front. And so that's our 6 flux values here. Left and right, they add up to 0, because you get 16 and minus 16. That adds up to 0, and then the back and the front are 0 fluxes. So it's really the only top and bottom surfaces that actually have a relevant flux. And so we take our minus 72 Newton meters squared per coulomb plus our 24, and we end up with a net flux of minus 48 Newton meters squared per coulomb. The net charge enclosed is going to be our net flux equal to our Q enclosed divided by epsilon naught. So you basically just take our epsilon naught times our flux, and that gives us our charge, and that's minus 4.25 times 10 to the minus 10 coulombs. Yes.
So the reason why left and right is the same is because in our given electric field vector, it's a constant, whereas top and bottom are variable.
Yeah.
Okay.
Yeah. I want you to study this particular problem. I really do. If you didn't work this problem out, if it was too daunting to you, I really want you to work it out. It's worth your time to go through it. Okay? Because this problem right here, all other geometries aside, this problem here perfectly demonstrates everything that I want you to know about flux in terms of its mechanisms. Yes?
And then, adding on to what he said about like in the y direction, the x direction being constant, so they would cancel out. If there was like a k component, like in z, and it was constant, then it would also cancel out. But if it was,
Well,
if it had a variable in it, then it wouldn't.
If we had a constant component of the field of the electric field,
Yeah.
it wouldn't yes, it would probably cancel out, yes. It depends on how things are oriented and what the function, yeah. I can't guarantee it,
Okay. Yeah.
okay? But yes, it would probably be that case. I wouldn't want to do that to him. That's horrible. That's one of those problems that'll take you 45 minutes to finish. Yes,
How many questions is the exam going to be?
15.
Do we have the whole class time?
You have 90 minutes.
Nice.
The timer on the test begins the minute you enter the password. And you have to be in the classroom to get the password. Actually, I don't know what the password is, and I gotta go look it up. Because I can't get into it without it either.
So we have to do 15 questions in 9 minutes.
I'm sorry?
We have to do 15 questions in 9 minutes.
Yeah. The test is actually written for about 40 to 50 minutes. I can finish in about 30.
You taking the
I
test
think
or
the
is
test-
it one of us taking the test?
This homework.
There's those people that finish the test in 45 minutes. Hmm? I don't know, I have a lot more.
I know you said that some of the questions are like fill in the blank. Is it like,
Very
For me,
few,
it's just
like
just
one or
a-
two.
do we have to for those questions?
Oh, no, I'm sorry, those are multiple choice.
I know it's not.
There's a lot that are actually.
It's pretty easy. Like this
Okay,
entire homework.
and so for the fill in the blank ones, like, I'm guessing it like asks for like a number that's in the middle of the
It'll
column.
it'll be a problem like this, and it'll say, what is the electric field for this configuration at a certain
I
distance
just
R?
didn't know where to go from there. 'Cause I
And then
tried to
once we
keep
find
the
out, we
four
can move
line.
on.
I think I had the integral, I had the integral of dA.
Do we bring our own
Supposed to do
scrap paper?
there.
Yes,
I don't
yes.
know, I just.
And make sure when you write it down, it's all legible. You guys are really good about making sure the homework is legible. Do the very same for them. Okay? And then take pictures when you're done, upload it to exam one work.
Weird question. Let's say like for epsilon naught, we use a slightly different value, because I was doing that on the homework for a little bit, and my answers were just slightly different, and like I fixed it, but let's say there's just something else somewhere.
What value were you using? Curious.
Yeah, she was like, I think it was just 8.8 times 10 to the.
Oh,
Yeah.
oh, yeah, no, that would be a little bit off.
Okay.
I think it was, I set the tolerance around the number, and I would think most of the time, your answer will fit within that tolerance. But
Okay.
there might be a chance where it doesn't. And if that's the case, it will mark it completely wrong.
Would you
This
go
is-
back and fix it?
Yes, I will.
Okay,
Yes,
that's.
I absolutely will.
So we can get partial credit?
Yeah, because I actually, that's why I call your score, when you get at the end of the test, that's your raw score. And your raw score is the lowest that you can get on the test. I won't take points away. I only add